Thank you. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students and for their persistence, not dropping this class and so forth. Just ask you to be with us today. Help us to, again, glorify you, Lord, in what we do. In the name of my prayer, Lord Jesus. Amen. All right, so I hope you don't mind I pushed the test back a week. I just don't think you guys are ready yet. You need to think about series some more. I think if you study series, power series, calculation another week, you'll get better at it. Also, I'm doing things in lecture which I don't know if they're exactly in the homework or not, but I will test on them. So I want you to try to understand the things I'm showing you in lecture because I think they're important, whether or not I actually have homework on them. Now, I'll try to, you can look at my old tests to kind of see what I'm talking about for one thing, in terms of the questions I ask about power series calculation. The other thing I guess I can try to do is to give you guys a quiz next week that kind of gives you a heads up on the sort of calculations that I think you ought to be able to do once you've seen me do them for a little while. We're still very much in the part of you watching me do them, and I'm trying to show you my tricks so that you can learn them and be like me, or something like that. I guess it's understandable why you guys don't want to do that. They're so mean. They're so mean to me. That comment about the phone last class, it was hurtful. Still coming to terms with it. Let's see here. So, so let me just talk to you guys about some things. So, of course, we proved this theorem last time, right? But one of the things I haven't told you yet, and I should mention just as a point of mathematical trivia, is absolute convergence is so very important. Why is absolute convergence important? You know, this theorem told us that if you have a power series and you have a point at which the power series converges, then we learned that the power series is absolutely convergent at every point which is at least as close as that point to the center, right? So why does that matter? Why does yes, we know absolute convergence implies convergence, but why is absolute convergence interesting? Why are we talking about it at all? Absolute convergence is interesting because of how weird things get for conditionally convergent series. So here's a theorem. This is, I can't spell Riemann. I think it's just one. I don't know. I can't remember if there's two N's or, I can't remember if there's two N's in Riemann or not. Oh well. Riemann, I'll put two N's. Riemann's rearrangement. Riemann's rearrangement theorem states the following. If, A naught plus A1 plus A2 plus dot 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 is conditionally convergent, then for each L in the real numbers, you can find a rearrangement let's say AI sub naught plus AI1 plus AI2 plus dot 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 dot, such that that is equal to L. What I'm saying is you can take the terms in the series and just by reordering the way in which they're added, shuffling a few to the front and pushing a few more to the back of the line, let's say, you can make it converge to L. What is L? A real number. Which real number? Any real number. I hope you see that that's very disconcerting. So what I'm telling you is, while it is true that we prove that the natural log of 1 plus 1 is equal to, what was it? Oh, no, that's not what I want to do. Well, it's true that we proved, that's not the one I'm thinking of. Remember the alternating harmonic series? Yeah, that's one. Alternating harmonic series was what? Sum k equals, say, 1 to infinity minus 1 to the k plus 1 over k plus 1, which is what? 1 minus a half plus a third minus a fourth plus dot, 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 dot. What I'm telling you is if you take those terms, all right, and I don't know if I can do it right off the top of my head, but you could, like, switch the order of the terms a little bit. Like, I don't know, say 1 plus a third, right? And then it's got to be some kind of infinite rearrangement. I can't do it. But if you were to reorder these terms, then, well, this is equal to the natural log of 2. We proved that, actually. If I was to somehow take these terms and, like, rearrange them, it wouldn't necessarily be the case. It still converged to the natural log of 2. That's the problem of rearrangement. I guess to make a better point, I should actually show you a rearrangement that converges to something other than the natural log of 2. I didn't actually have that prepared for today, so I might do well not to try to do that. Let me see if I can find it in the text right quick. I can't remember if he actually has an example where he shows you how that happens or not. Yeah, look here a second. It should be in where he discusses conditional convergence, rearrangement. Nope. Maybe he's got a homework problem on it. Well, oh well. I'll tell you what, guys. I'll look it up and I'll find you a link to an article which shows you an exact rearrangement of that. Okay, I'm not going to try to do it on the fly. It'd be a waste of your time. But trust me that you can, just through a different way of adding these, by rearranging the terms, you can get a different number. It's very weird. Yep.
What's the base of things? What does it say?
These are just, so here, I naught, I1, I2, and so forth. These are elements of, like, the set 0, 1, 2, 3, but not necessarily in the same order. Yeah, it's fine, but it's a good question. I mean, so what I'm trying to say is you reindex the way you're adding them. It's a rearrangement. So the other theorem, though, is that if you have absolute convergence, rearrangements, like the order in which you're adding them, if you change the order, even if you change it in an infinite way, like if you swap the order of infinitely many terms in the sum, you can't change the outcome. It still converges to the same thing. So absolute convergence is so important because as we do calculations with power series, we like to rearrange terms. And the fact that we have absolute convergence means we can rearrange with immunity without getting into trouble. So, sorry, again, I will send you a link to an actual rearrangement. I used to teach out of Stewart's calculus. In Stewart's calculus, he actually has an explicit rearrangement that shows you how to get the alternating harmonic series to converge to 3 times the natural log of 2 by just rearranging the terms. But it's sneaky. It is sneaky how to do that. Okay, so thankfully that's not going to happen over here, so I don't have to worry about which one I'm adding first or second or third, because I'm dealing with power series which are absolutely convergent, so I can add them and subtract them in whichever order I want, and I won't change the outcome because I have absolute convergence. Excuse me. Let me talk through this example and then I'll do new ones for you guys. So here I said, okay, I have x e to the x. I wanted to find the power series for this centered at 3. So I did my usual trick. I added and subtracted 3, right, in here and here. And so then that gives me x minus 3 times e to the third times e to the x minus 3, and then 3 to the 3 times x to the minus 3. But, well, the circled ones, that's a standard thing. That's an exponential. I can substitute x minus 3 into the Maclaurin series for the exponential, which we already know. That's what I do here and here. Then I multiply things out. So like this gives me k plus 1, And that one just gives me the 3e to the 3 over k factorial. And then I want to add them. I want to put them together. I want to make one nice simplified final answer. I can't quite do that here because why? I've got k plus 1 as my power on this term, and I've got k as my power on that term, right? So to make these come together, I have to reindex this sum. So I make a substitution, j equals k plus 1. And just to make things look the same, I put k equals to j over here, you know? And then they match, because then I've got to the jth power, I've got to the jth power. If j is equal to k plus 1, that means k is equal to j minus 1. And so that k becomes j minus 1 factorial, and like that. And you see now I can almost add these, but what's the problem? Yeah, I got 1 here. And what? Yeah, the range is not quite right. See, this one's got one extra term. It's got a constant term, right? So what I do is I just peel that off. I peel off the constant term and I write it first, 3e to the 3. That's what breaks the pattern that unifies these two sums, right? But otherwise, now they're apples and apples. I can add them. So I got e cubed. I factor it out, and I have 1 over j minus 1 factorial plus 3 over j factorial. And there you go. That's the power series expansion for x e to the x centered at minus 3. So have you guys done this in high school, or? Yeah. Now, did you do it that way, or did you use Taylor's series?
We use Taylor's series.
So you did it like this over here. You said f of 3 plus f prime of 3 times x minus 3. Is this faster?
The way my teacher does it that way is faster, but
Yeah.
he does it, but he allows us to do it a lot different ways.
Mm-hmm.
He wants us to play with the numbers first.
Play with the numbers first? I guess this one's not too bad. You can differentiate x e to the x. You'll have power product rule, and then product rule, and then product rule, then product rule, then product rule, then product rule, then product. And it's not.
I actually tried to do that first, and then he was like, "Don't do that." And he said, "Just derive, start doing it like that."
Huh. Okay. Let's see here. And then we have this. This is our answer. Here's the Maclaurin, the Taylor series centered at 3. And just as a fun application of this, of course, we can do something silly like calculate the 25th derivative of the function at 3, right? So that trick again. So what I do is I just compare the 25th coefficient divided by 25 factorial to what I have here, which is that, right? And then you multiply by 25 factorial. Remember, 25 factorial is 25 times 24 factorial, so the 24 factorials cancel, leave you the 25, and the 25 factorials just cancel, leave you the 3. And so the 25th derivative of this function at 3 is 28 times e cubed. Yay. So, again, I would remind you on the test, if I ask you to calculate like the 30th derivative of something, I probably don't actually want you to differentiate 30 times, right? Probably not. This was the example that I gave before that, which is kind of a baby example. You can either use the Taylor series and just, for e to the x, you could just differentiate and plug it in, right? Or you can use my adding 0 trick to do a substitution to get the series like that. Yeah. Yeah. Because this one has the product of x minus 3 with the exponential. So this times that gives me k plus 1. Whereas this one is coming from just a constant times the exponential series. So that you don't ever multiply the powers in the Maclaurin series, in the exponential series, yeah. Well, j is just a notation. It's just a dummy variable of summation. So, the k or the j, they're not like reserved notations or something. I'm not sure I understand your question yet.
I think she's wondering why j is equal to k on that side and j equal to k plus 1.
These right here, these are definitions. I'm saying let. We usually say it this way, let. So it's a philosophical thing. I should say let j equals to k. That would be maybe clearer in your mind.
So
because I want to combine the sums in the step after that. I guess I could have left it k and then just said, well, you know. Yeah.
When you find the 25th derivative of f of x, where does the 3 e to the 3 before the summation come in, or does it not?
The 3.
3 e to the 3 at the bottom where you found the series. Are you supposed to add that in there?
Why would that matter? The point is, f of x, right, is equal to the sum by Taylor's theorem, k equals 0 to infinity, of the kth derivative evaluated at 3 over k factorial times x minus 3 to the k power. So if I want to understand what's the 25th derivative of the function, I need only concern myself with the coefficient of the 25th power of x minus 3. What happens on the 0th term or somewhere else, I don't care. I mean, I'm not sure I understand your question yet.
I think it is.
Okay. So generically speaking, our current pursuit is just to try to understand series calculation better. So I'm just going to keep showing you this amalgam of examples until I've shown you all my tricks, basically. And the theme of these examples, of course, is manipulation of series. All right, how to calculate with series. That's basically it. So let me show you another example. How about this? Find Maclaurin series for f of x equals to x plus x squared over 1 minus x cubed. If you try to use the Taylor series on this, no, don't do it, right? That's quotient rule upon quotient rule upon, oh, it's awful. Here's how I do this problem. So what you want to do is use what you know. What do we know? We know geometric series, right? And if you just do that, you can identify that this is these are geometric series, right? If I undo them, this is what? This is the sum, x times x cubed to the k-fold power, k equals 0 to infinity, plus the sum, x squared times x cubed to the k-fold power, k equals 0 to infinity. Why do I do, I mean, how did I get, what's my internal logic here? So I have what? I've got a equals to x squared. My ratio is x cubed, right? And how about this one? Here I've got a equals to x, and I've got still the same ratio, right? I'm not done yet. Those aren't power series. When is it a power series? What is a power series? Power series is something of the form a sub k times x minus x naught to the k power, right? That's a power series until I have rewritten the expression so that it looks like that. And it can be the sum of a couple series like that. You don't have to have one universal formula for the whole thing, right? The fact that I couldn't group this term into the other ones in the same pattern doesn't matter. That's not the point. The point is that the power function has to be written multiplicatively, and the coefficient has to be out front. So like this isn't quite done yet, right? Now to finish it, what are the finishing blows here? Let's see here. K equals, sorry to be so violent. Let's see here. This is x to the 3k plus 1 plus the sum k equals 0 to infinity of x to the what? 3k plus 2. Is there any overlap between those sums? This problem has what I might call threeplicity. We worked an example before with fourplicity, remember? Any integer can be broken into multiples of 4. 0, 4, 8, 12, 1, 5, 9, so forth. 2, 6, 10, 14, 3, 7, 11, right? In the same way, any integer can be broken into something like, I might call it 3z, or 3z plus 1, or 3z plus 2, right? 0, 3, 6, 9, 12, blah, 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 or 1, 4, 7, 10, 13, so forth. Or you got your 2, 5, 7. I just did something wrong. 2, 5, 8. I can't add. 11. My point to you is you've got like these kind of numbers in here, right? You got these kind of numbers over here. There's no way that those overlap. Those are disjoint cases. So that's the answer. I can't simplify that further. That's it. Now, if you want me to write it out in terms of plus dot dot notation, I could do that. What's the lowest term here? X, right, x. What's the next one from over here? X squared. Let me color code it. Yeah, the marker's just about dead. Plus what? Next one here is plus 3. 1 plus 3 is what? X to the 4th. What's the next one and the other one? K equals to 2, x to the 5th, yeah. Plus K equals to, what is it? 7? Plus, yeah. 10, yeah. Yeah.
Can you let A be like x squared plus x? Do you understand?
Can I?
A be x squared plus x, and R be to the third power?
Yeah, you could do that, but then you'd have to multiply, right?
Yeah.
So yeah, the other way you could, of course, have gone directly to x squared, let's see, rather x plus x squared times the sum. I mean, you could look at it like that too, right? Because you could say x plus x squared over 1 minus x cubed is equal to x plus x squared, parentheses, times 1 over x, 1 minus x cubed, right? Yeah, you could have done that. And then, of course, this would be that. Or you could just, I mean, yeah, there's other ways to look at it, but here, let me count the roses while we're at it here. So if you had to explain to me what are the derivatives of this functions in all order, you could tell me, right? F of, let's see here, 3k plus 1 at 0 is equal to f of 3k plus 2 at 0, which is equal to 1, right? For k equal to 0, 1, 2, whatever, right? And on the other hand, f of 3k at 0 is simply equal to 0 for all k 0, 1, 2, and so forth. So the function is 0 at 0. The third derivative is 0. The sixth derivative is 0. The ninth derivative is 0. The 12th derivative is 0. The 15th derivative is 0. The 18th derivative, you get the point. You can see all of that. And by the way, we saw all of that without differentiating once. Do you see the power of what we're doing? Understanding what we already know and using it is very, very useful. I mean, yes, I could use Taylor's formula, but it's terribly inefficient for this problem. All right, let's look at another example. All my examples tend to be centered at 0. Let me try to do something a little bit different. Find series for f of x equal to 1 over 1 minus, let's say, x. That's still too simple. Let's make it more difficult. Let's say x squared. Centered, oh, fine, x. X not equals to, I guess I'll start simple, 3. I like 3. 3 is fun. Now, admittedly, the gentleman in the back would be right. I could use Taylor's theorem on this one. It wouldn't be too bad. True, but I won't. So what I want to do, right, is if I'm trying to center this, which means I want x minus 3 to the k type stuff, right? I'm looking to make that happen. To make that happen here, what do I do? If I put that, if I change my minus x to minus x minus 3, what did I have to do? I just did what? Yeah, I added 3 there, so I have to do what? I have to subtract 3, right? Let's simplify that. What's that equal to? Well, this is equal to 1 over what? Minus 2 minus x minus 3. You're like, oh, man, I want a 1 there, right? I'm trying to use geometric series, right? Our goal is to massage this thing until it looks like a over 1 minus r. Because once I have that, I know what to do. How do you change a 2 to a 1? Yeah, how about minus 2, right? Factor out a minus 2, how about that, yeah? Then I got a 1. But to be fair, I've got what? Plus 1/2 times x minus 3. That's fine. I can deal with that. So now I have a equals to minus 1/2, and I have r of what? Minus parentheses x minus 3 over 2. That's my ratio. And I apply the geometric series result again. Sum k equals 0 to infinity. Minus 1/2, parentheses, minus 1/2 times x minus 3 to the k power by the geometric series result. When is this step legit? Not true for just any x, right? Like this one wasn't true for any x either. What was this? This lovely formula is only legitimate where? This is for what? I should have said that. You guys got to keep me more honest here. I know I said I'm trying to focus more on calculation and less on domain, but come on, let's at least give a little lip service to rigor here. This is only for the absolute value of x less than 1, right? Because if I have this, if I want r less than 1, what does that mean? I need x cubed less, so that's just same as just x. In other words, the interval of convergence here is minus 1 to 1. By the way, I know there's something else I should mention. I was telling you guys, got to use ratio test, got to use ratio test. Well, no, you don't. I know the interval of convergence of this series without further calculation, without ratio test, without anything else. I already know the interval of convergence of this is minus 1 to 1. How do I know that? It's the sum of geometric series which only converge from minus 1 to 1. The endpoints correspond to ratio 1. I know that diverges from previous work. I don't need to use ratio test or something to figure that out. I don't need to test endpoints because this is geometric. And I have data from the geometric series result that I can use here to save myself work. Isn't that nice? Remember how much we had to do a lot more thinking in the other class about ratio test and testing endpoints, right? Now, if you integrate or differentiate in conjunction with the geometric series result, then you got to check endpoints again because integration and differentiation can mess with your endpoints, all right? Okay, so this is legit for what? R less than 1, which is what? Now it's kind of interesting, right? That's the absolute value of x minus 3 over 2. less than 1. Which is what? In other words, the interval of convergence here is going to be what? 2 to 4, right? Because you go, your 3 is your center, and then you go plus or minus 1. Oh, man. This is why we can't have nice things. Let's see here. Now you got me thinking about my phone again. Shaking my confidence. Minus 1 to the k plus 1 divided by 2 to the k plus 1, parentheses x minus 3 to the k power. There you go. Only from 1 to 5. Not included. Geometric. Lose the endpoints. Any questions? Yeah. Oh, 3 plus 2, 3 minus 2. So this tells me minus 2 less than x minus 3 less than 2. And then adding 3 gives me 1 less than x less than 5. Usual song and dance. Want to see something weird? Doesn't sound good? What if we had something like this? Let's just play for a minute. Check this out. Well, I can rewrite this, right? This is 1 over 1, let's see here, minus x times what? Yeah, 1 minus x, I suppose, right? So I can apply the geometric series result, right? What's this? Fine, I guess that's x minus 1 to the k, and I can split off a minus 1 to the k power out here, right? That's weird. What's the, where's this converge? You need r less than 1, right? So that's the absolute value of x times the absolute value of 1 minus x less than 1. What's that? I guess it's something like x squared minus 1, right? No, x, what is it? It's man, I guess it's x squared minus, the absolute value of x squared minus x less than 1. What does x squared minus x look like anyway? I guess if I was to graph this, y equals x squared minus x is what? It's got a 0 at 0 and also 1 at 1. It's a parabola. It opens up like so. It's, what's its vertex? 1/2, right? And that's a quarter minus, I think it's a half minus a quarter, right? because a half squared is a quarter minus a half is minus a quarter. So the vertex is a half minus a quarter. So if you, just a second, Travis, if you look at this, then this inequality, I guess, is just where, oh, I guess that's not too bad. That would be like just this in here. Oh, that's quirky. It's actually not too bad. Weird. Yes? Curses.
Isn't it supposed to be x minus x squared? Supposed to one?
X minus.
Yeah, just like multiplying the x times.
Oh, well, that's the thing. You could go either way, right? Because this is equal to x minus x squared. The absolute value is, it would turn it over. But you're still just looking distance from the x-axis to be. You're looking for the whole graph that's less than 1 unit of distance away from the x-axis here to solve the inequality. It's a quirk. I mean, I've done this example before, and I haven't necessarily gotten just one. So like, apparently, whatever this number is, say A, whatever this number is B, the interval of convergence happens to be an interval. It's A to B, right? Why shouldn't I do this example in here? Can you tell me why? A different way of saying this. Why should this calculation give you great pause before you say other things about it? Like, is this a power series? Is my first question. I hope you realize this is not a power series. You might call it a biseries or something. I don't know. It's got two centers. It's centered at 0. It's centered at 1. That's weird. We got lucky. Like, I've studied these things before. Usually you get intervals of convergence that aren't intervals of convergence. I mean, you tend to get places where it converges. Like, you've got someplace over here where it converges. Maybe you got someplace over here where it converges. They can be disconnected. All kinds of weird stuff can happen. So how would you make this into a power series? It depends on what center you want, right? You got to pick a center. You could pick 0. You could pick 1. You could pick some other point, right? But this is not a power series, even though this is a legitimate use of the geometric series result, right? So where do you guys want me to? I mean, we could center it somewhere. Where do you want to center it? How about at 0? Yeah. Oh, maybe that's a bad choice. Well, fine. At x equal, if I choose x not equals to 0 as my center, then well, that's unpleasant. Why is that unpleasant? Oh man, that's really unpleasant. I'm trying not to be that unpleasant today. I have visitors. Let me stop. My point is to you that we shouldn't be bothered that it doesn't line up with our general theorems about domains for power series, because this isn't actually a power series. It's like a power series, but it's not a power series. That's why, guys, it's so important when you try to do calculations, if you're going to use the theorems about power series, do make sure you actually have an honest-to-goodness power series. Otherwise, you can get yourself into trouble. Let me see here if I can't. Let's see here. I guess it's not too bad to center this at 1. We have f of x 1 over 1. Fine. I don't know. I'm trying to think of a best way to explain this. I don't know. I guess I'll try for the Maclaurin series. Fine. So let's see here. This is minus x squared minus x, right? I'm sorry, I'm an idiot. Minus x squared. There we go. And I'm just going to use very low tech stuff here. This is 1 plus parentheses x minus x squared plus what? X minus x squared squared minus x squared cubed, and so forth, right? Geometric series. And this should be for, again, for the absolute value of x minus x squared less than 1, that's valid. um, And then but the thing that makes this kind of a malevolent example is, yeah, that's fine, right? But this one, how's that work? That's x squared minus 2x cubed plus x to the fourth, right? And how about this one? X cubed minus 3x squared times x to the fourth plus 3. What's the odds here? 6 maybe? I should probably, I'm sorry guys, let me not cheat and actually write it out. So that's x cubed minus, well, I should say plus 3 times x squared times minus x squared plus 3 times x times minus x squared squared, and then plus minus x squared cubed. That's the, so this is what? This is x cubed minus 3 x to the fourth plus 3 x to the fifth minus x to the sixth. So you see what happened here? And then what? Is that it? Now, if you think about it, if you go to the fourth power up here, if you go to the fourth power, what kind of terms do you have there? Well, you've got things that go from what? From like next one goes from x to the fourth to what? To x to the eighth, right? So there's also an x to the fourth term in the next one. And so as you try to rearrange these, you got to think about combining not just adjacent things, but like, let's see here. So all I can tell you with confidence is that this is 1 plus x. The x squareds cancel. I think that's the only x squareds I have, right? So then when we get to x cubed, we've got minus x cubed. Is there anything else x cubed wise? No, I think that's it. But in order to figure out x to the fourth, I'd actually have to go to the next thing, and I'm just tired of this. So. What else can you do with series? So we can multiply series. We can do these substitution tricks like I've been showing you. Do you guys know how to divide series? Let me say that another way. If you have 1 over a series, what is it equal to? For example, 1 over 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus dot, 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 right? What's this equal to? You don't know? Can't you see it? It's obviously 1 minus x plus 1/2 x squared minus 1 over 3 factorial x cubed plus dot, 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 dot. Now, of course, I'm, as usual, the man behind the curtain, so I know things because this is my example. And so I recognize this is 1 over e to the x is equal to e to the minus x. Okay, so I'm cheating, yes. The question is, how would you do that for a generic series, right? Like, how do you get from here to here in terms of some calculation? Yeah? How do you, but what series does that give you? If you take the reciprocal of a series, how do you get the new series? How did we do it before? If we had like, well, I can't do that. Sorry, guys. Is there some kind of long division we can do? What are we trying to do? We're trying to divide this into 1, right? So where should the 1 go? Right in here, right? And then out here we put the 1 plus x plus 1/2 x squared plus dot, 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 dot. I'll just do that much. So what's the first thing I put? Multiply this times that. I mean, multiply this times something to get that. What do I need to put? 1, right? That puts what down here? 1. Right? Take the difference. We get what? Minus x minus 1/2 x squared plus dot, 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 dot. So then how do I get this minus x? Something times this gives me that. What do I put there? Minus x, right? Now, what do I put down here? Well, minus x minus 1/2 x squared. Well, yeah, minus 1/2. Excuse me, math. Minus x squared. Sorry, having technical difficulties. Minus x squared minus 1/2 x cubed, yeah? Take the difference. What do you get? The x's cancel by our construction, and we get 1/2 x squared stuff, right? So what's the next thing you put? Plus 1/2 x squared, right? And then that would put you 1/2 x squared down here, stuff, and you keep going. So you can do unending long division to reciprocate a series. Right? I'm not talking about the u as you currently exist. I'm talking about the u after you've studied what I just did. Right? I mean, I personally, I don't know, I will forget this personally from time to time. Can we try it out on something else? I think I'm out of time, but yeah, pretty much. Anyway, I hope you learned something today. If you have questions about the math at Liberty, I'm happy to talk to you. If you guys are CFOC, you can cut it off. Thanks.